we defined limits as x approaches infinity. Today we're going to look at the limit laws at infinity, which leads us to a new theorem that will allow us to calculate a lot of limits that would be difficult or impossible to calculate otherwise. We're going to look at 2 or 3 examples, then finally we will define what it means for a limit to grow arbitrarily large as x approaches infinity. Almost all of the limit laws will work with x approaching infinity as well, except 9 and 10. They don't work. So it's easy to see why 9 and 10 won't work, because law 9 is that the limit as x approaches a of x to the n equals a to the n. But if we replace this with infinity, that means that x to the n equals infinity to the n. And what is that? This doesn't mean anything. That doesn't make sense. And then, so law 10 says that the limit as x approaches a of the nth root of x equals the nth root of a. But again, if a is infinity, then what would the nth root of infinity be? Again, that just doesn't make sense because this isn't a number. But the remaining laws that we went over a few weeks ago can be proven. And we're not going to do that now, but if you want to see it, we can go over it some other time. Just let me know. There's one result in particular that we can use when x approaches infinity. We can combine rules 6 and 11 with the result that we just showed, that the limit as x approaches infinity of 1 over x is 0, to make a very useful new theorem for analyzing limits. So law 6 says that the limit as x approaches a of f of x raised to the nth power equals the limit of f of x as x approaches a raised to the nth power. Remember, this is true when n is a positive integer. Law 11 says that the limit as x approaches a of the nth root of f of x equals the nth root of the limit as x approaches a of f of x. N is a positive integer. We also have to stipulate that if n is even, then the limit has to be greater than 0, because otherwise the result would be complex. So notice how subtly different these 2 rules are from these 2 rules. With limits, it's always about calculating near some value, never on the value. So that's why it's okay to, for instance, the whole reason we're talking about this is with derivatives. If you have that f of x plus h minus f of x over h, the whole reason it's possible to do this is because we're never actually dividing by 0, right? The same thing is true here. It's always possible to calculate near the point, but maybe not on the point. So the problem with these is that we're claiming, law 9 claims that the limit of x approaches n equals a raised to the n, and same thing here. But we can't do that if we're approaching infinity. That doesn't make sense. But with these 2 laws, we're not claiming what happens at a. We're claiming something that happens near a. So you can always do this. So you can see why we can replace this with infinity and this with infinity, because we don't have anything confusing here. Because the limit as x approaches infinity of f of x to the n never equals infinity. It's just getting bigger and bigger. That's always possible. And same thing here. If this is infinity, we can always look at f of x as x gets bigger. So this never fails to mean something. And it's the same thing here. It's the difference here between making a statement about the value at a or at infinity versus talking about what happens as we approach a or approach infinity. So these 2 rules work, even though these 2 rules don't. So we can combine law 6 and law 11 with the result from above to prove a very useful theorem. If r greater than 0 is a rational number, then the limit as x approaches infinity of 1 over x to the r equals 0. And if r greater than 0 is a rational number such that x raised to the r is defined for all x, then the limit as x approaches minus infinity of 1 over x to the r is 0. So what this theorem says is that the limit of 1 over any power of x as x approaches infinity equals 0. So if we can manipulate our function algebraically into powers of 1 over x, we can use this theorem to dramatically simplify the calculation of the limit. The reason for this extra little detail here when we're going to minus infinity is because it's possible if x is negative that x raised to the r is not defined over the reals. So for instance, x to the 1/2 equals the square root of x. This isn't defined if x is less than 0, but x to the 3rd is defined even for the negative numbers, right? The cubed root of -1 equals -1. So it depends on what the rational number is, whether this will work for minus infinity, but it always works for positive infinity. Okay. So let's look at how this works. So let's evaluate the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So notice, first of all, our instinct might be to start applying our limit laws, right? Apply the quotient law and then the addition and subtraction laws to get the limit of 3x squared minus the limit of x minus the limit of 2 over the limit of 5x squared and so on. You can't do that because the limit as x approaches infinity of 3x squared doesn't exist because it shoots off to infinity also, okay? So the limit laws won't apply here yet. So always be careful about that. You've got to be careful that the limits exist before you can use the limit laws. So what we can do here is divide both the numerator and the denominator by the highest power of x that occurs in the denominator. So we're going to rewrite this by multiplying it by 1 over x squared over 1 over x squared. We can always assume that x is positive because we're looking at where it goes as it gets very large, so we don't have to worry about 0 here. So if we divide through, we end up with 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. Now we can apply the quotient rule here because the limit of 1 over x as x approaches infinity is going to be 0, and same with 1 over x squared. So now we can use our limit laws. So let's do the quotient rule first. So we have the limit of the numerator over the limit of the denominator. That's the quotient rule. We're always talking about x approaches infinity. So if we apply the addition rule, the subtraction rule, and the constant multiplier rule, we end up with this. So now we just apply law 7, which is just the constant law that the limit of 3 is 3, and our new rule to get 3 minus, this is 0, minus 2 times 0 over 5 plus 4 times 0 plus 0 equals 3/5. And then a similar calculation, if we did this with minus infinity, would show that the limit as x approaches minus infinity is also 3/5. And here's this function on Grapher to see what it looks like. The function approaches the horizontal asymptote y equals 3/5. So one more thing to notice about this. This isn't a rule, but it gives us a good clue as to what's happening. We could have just read off the 3 over 5 right here, because what happens as x approaches infinity, the higher powers dominate everything else. So x squared is increasing way more quickly than x. So basically, these just all become irrelevant, which is what, when we divided through, that's what we ended up with, right? 4 zeros. And then these are rising at basically the same rate, even though a slightly different ratio here. So what this function approaches as we go out to infinity is just 3 over 5. Okay, let's do a couple more examples. What about the square root of 2x squared plus 1 over 3x minus 5? Let's find the horizontal and vertical asymptotes of this function. So again, same as the last example, we can't just start applying the limit laws because as x approaches infinity, this goes off to infinity and that goes off to infinity. So again, let's try some algebraic manipulation. So let's try to just divide through the top and bottom by the largest power of x in the denominator, which is 1. So if we multiply the top and the bottom by 1 over x over 1 over x. So if you're going to multiply this radical by 1 over x, that would be the same thing as the square root of 1 over x squared. So that'll take the x squared inside here. So we'll end up with the square root of 2 plus 1 over x squared. And then multiply this through, and we end up with 3 over x minus 5 over x squared. Oh, let's do this again. I forgot what we were dividing by. So the top is 2 plus 1 over x squared, but we're only dividing by x, so we end up with 3 minus 5 over x. Now we can apply the quotient law as long as this does not approach 0. So that equals the limit. Again, it's always x approaches infinity of the square root of 2 plus 1 over x squared over, whoops, the limit of 3 minus 5x. And then I'm going to combine several. Now we can use the root law and then the addition law and the constant multiplier law. So this equals the square root of the limit of 2 plus the limit of 1 over x squared over the limit of 3 minus 5 times the limit of 1 over x. Now, using the constant law and our new theorem, we can just calculate that's 2. That is 0. This is 3. And that is 5 times 0. Equals square root of 2 over 3. Okay, so y equals square root of 2 over 3 is a horizontal asymptote as x approaches positive infinity. Now, what about when x approaches minus infinity? We have to remember that when x is less than 0, then the square root of x squared equals the absolute value of x, right? Because we got rid of the minus sign here. So in this case, when we're looking at x less than 0, when we divide the numerator by 1 over x, that equals minus 1 over the square root of x squared. So now we can move it in, and then we get minus square root of 2 plus 1 over x squared. Okay, this is the numerator. So the point here, this minus sign is going to carry all the way through as x approaches minus infinity of f of x. This using the quotient rule, the addition rule, the constant multiplier rule, same as before. But we have to remember that the minus sign sticks through. So then this is 0, and we have minus square root of 2 over 3. So that means that there's another asymptote in this function at minus the square root of 2 over 3. Okay, that's interesting. So this function has 2 horizontal asymptotes. Now, are there any vertical asymptotes? Well, there's likely to be a vertical asymptote when the denominator is 0. So in other words, there's likely to be a vertical asymptote at x equals 5 over 3. Now, in this case, the denominator here is 3x minus 5. So if x is greater than 5 over 3, then the denominator is going to be positive. But if we approach 5 over 3 from the left, then this will be minus. Then the denominator will be minus. So that means that when we have the limit as x approaches 5 over 3 from the right, the denominator is going to be getting closer and closer to 0, but always be positive. That means the whole function will be positive, so it's going to be going up to positive infinity. And then as the limit as x approaches 5 over 3 from the left, it's the same, it's going to grow, but the denominator will be negative, so the whole function will be negative, so it's going to be going down the other direction. So the limit as we approach 5 over 3 from the right of f of x equals infinity, and the limit as we approach 5 over 3 from the left equals minus infinity. Okay, so there's a vertical asymptote at x equals 5 over 3. So let's see what that looks like on Grapher. So we have 2 horizontal asymptotes and 1 vertical asymptote that goes in opposite directions. So I want to point one thing out again about this. It's really interesting that because this is x squared inside and the square root of that, again, the powers of the numerator and denominator are the same. They're both basically x. So they're both approaching infinity at the same speed, and that means that we're dividing one over the other so that as we approach infinity, the ratio of these two is getting closer and closer to one number, the square root of 2 over 3. What's interesting about that is that if they're growing at the same rate, then we can approach any number. We can come up with a function that approaches anywhere. So it's kind of interesting. It's not that the options are either, you go up this way, or you go down this way, or you just approach 0. You can approach any number you want. It can be anything here that the function approaches. I think that's interesting, that if the numerator gets big faster, then it's going to go off to infinity. But if they are growing at the same rate, then there's a very delicate balance between the two of them that can land us anywhere on the number line. And this boundary between when is a series converging toward a number and when is it not, when does it end up growing without bound, is a fundamental question in real analysis. So let's just look at one more example that sort of shows how it can be difficult to see. If we have the limit as x approaches infinity of the square root of x squared plus 1 minus x. Now, in this case, both this term and this term are both approaching infinity as x approaches infinity. So it's not easy to see what's going to happen here, because what we're getting is infinity minus infinity. There's no way to define this. And we cannot, because of that, we can't apply the addition law because the limit of each of these does not exist. But again, the question is, can we use algebra in some way to manipulate this in some way that will allow us to see what the answer is? Okay, well, let's try multiplying through by the conjugate here. That will get rid of the radical on the top. So this will equal the limit, again, x approaches infinity, the square root of x squared plus 1 minus x. We're going to multiply it by the conjugate over the square root of x squared plus 1 plus x on the bottom. Okay, so we're going to multiply this. This gets rid of the radical, and we have x squared plus 1. The middle terms cancel, and then we have minus x squared here. That's convenient. These cancel. And then on the bottom now, we have the square root of x squared plus 1 plus x. Okay, so this is helpful because we got rid of the radical in the numerator, but we still have this still doesn't help us because we're still approaching infinity. That means both of these approach infinity, so we're not there yet. Now we have to multiply through in a way that will get us to something that we can use our new theorem for. So if we multiply, remember the square root of x squared is just x, so if we multiply the top and the bottom by 1 over x, we have, then I'm going to go ahead and, oh, actually, I shouldn't have done it this way. Let me do this again. Let's leave the limit outside first. It'll make it easier to see. So we're multiplying the top and the bottom by 1 over x. So we have 1 over x on top. And on the bottom now, we're multiplying 1 over x times the radical x squared. So again, we can move the 1 over x squared inside the radical, and we have the square root of 1. X squared over x squared is 1 plus 1 over x squared plus 1 over x. Oh, I did it again. We're multiplying by 1 over x, so x times 1 over x is just 1. Sorry about that. Okay. So now we can move the limit up and down and see what happens. So we have the limit of 1 over x over, and now I'm going to do several rules. So we're going to use the radical rule, and then the constant rule, and then our new theorem, and then the constant rule again. So we end up with the square root of the limit of 1 plus the limit of 1 over x squared plus the limit of 1. And all of this part is inside the radical. So now that equals, this is 0. The limit of 1 is 1. The limit of, as x approaches infinity, of 1 over x squared is 0. And the limit of 1 is 1. So that just equals 0 over 2 equals 0. So isn't that interesting? This is infinity minus infinity. At infinity, this is infinity minus infinity. You could end up with any number here. What you end up with, in fact, is 0. The reason is this is only barely bigger than this one. So every step of the way, they're getting closer and closer as you're approaching infinity. This difference of 1 is getting less and less significant. Okay, a couple more things. So the function y equals e to the x has a horizontal asymptote at y equals 0. So you probably know what this looks like. There's 1. So e to the x is increasing as x gets bigger, but it's approaching 0 as x approaches minus infinity. The limit as x approaches minus infinity of e to the x equals 0. Another interesting point here is that if we look at a table of the values, we can see that this function actually approaches 0 very quickly. And that's another issue in real analysis, which is what establishes whether a series will converge or not, is how quickly it goes to some value. So this function gets down to 0 really quick. It's really approaching it fast. But there are other functions that might just barely be getting down there, just as shallow as possible. And there's some boundary at which they'll never meet. But if it's just a little bit inside that, then they will meet eventually. But that's the important question in real analysis is, where is that boundary? And if it's inside that boundary, they will meet. If it's outside that boundary, they won't. And this isn't only true of e, this is actually true of any function a to the x, as long as a is greater than 1. Now, what about the limit as x approaches 0 from the left of e to the 1 over x? What's this going to look like? If we let t equal 1 over x, then we know from our theorem that if t approaches minus infinity, then 1 over x is going to approach 0 from the left. Okay, so that means that from what we just did here, we can rewrite this function, the limit as x approaches 0 from the left of e to the 1 over x, we can rewrite that as the limit as t approaches minus infinity of e to the t. And now this is what we just did. So that equals 0. So it's very interesting. You can see that we can manipulate these things in a lot of different ways. This is a very interesting thing. We actually rewrote what it is that we're approaching from 0 to minus infinity. So there's a lot to consider here. Okay, one more example, very quick. What about the limit as x approaches infinity of sine of x? Now in this case, sine just goes up and down forever. So as x approaches infinity, sine is forever going to oscillate between positive 1 and minus 1. So it's never going to settle on a single number. So this limit simply does not exist. Okay. Now finally, what about when a function grows arbitrarily large as x approaches infinity? We can also say, sort of combine the last two things that we've been talking about, that the limit as x approaches infinity of f of x equals infinity means that f becomes large as x becomes large. So that's basically any normal function that goes up to infinity, right? The same is true with the other symbols in any combination. So these all mean the same thing, that if x gets large negative, then f of x goes up to infinity, or f could go down to minus infinity, and so on. So what about the limit as x approaches infinity of x cubed and the limit as x approaches minus infinity of x cubed? Well, when x becomes large, then x cubed also becomes large, right? 10 to the third equals 1,000. 100 to the third equals 1,000,000, and 1,000 to the third equals 1,000,000,000. And in fact, we can see that we can make x to the third arbitrarily large by just increasing x. The more we increase x, the more x to the third increases. So that tells us that the limit as x approaches infinity of x to the third equals infinity. X cubed gets smaller as x approaches minus infinity, right? So minus 10 to the third is minus 1,000, and so on. So the limit of x to the third as x approaches minus infinity is going to be minus infinity. And that function just looks like this. It goes down, pauses, and then goes down, right? So it goes up that way, goes down that way. So I just want to point out again, we were talking about the limit as x approaches infinity of sine x. Infinity, again, is still not a number, right? This is just describing a certain behavior. It's a particular way that this limit does not converge. The limit as x approaches infinity of sine x also does not converge But again, it does not converge in a different way from this one. So you cannot say that this one equals infinity. It doesn't equal infinity. It's never above or below 1 and minus 1. So this limit does not exist, but it also does not converge in a different way from one in which we would say that it approaches infinity. What about the limit as x approaches infinity of x squared minus x? Now, again, we can't use the subtraction rule here because these two limits the limit as x approaches infinity of x squared does not exist, and same with x, because we end up with infinity minus infinity again, and that's not defined. But here we can do a little algebraic manipulation once again. Factor out the x. We have x times x minus 1. Now this goes to infinity and this goes to infinity, and if both x and x minus 1 become arbitrarily large, then their product also has to become arbitrarily large. So the limit of this has to equal infinity. So let's try one more. The limit as x approaches infinity of x squared plus x over 3 minus x. So as we saw before, the thing to do with a rational function is to divide through by the largest power of x. So we multiply the top and the bottom by 1 over x, and we have this is x plus 1. 3 over x minus 1. So now, if we look at the limit of each of these, using our rule, as x approaches infinity, 3 over x is 0, and minus 1 is minus 1. So the limit as x approaches infinity of 3 over x minus 1 equals 0 minus 1 equals minus 1. Okay, that's the denominator. So the numerator is going up to infinity. The denominator, though, is approaching minus 1. That means that this whole function is getting larger in a negative way. So this will actually equal minus infinity. Okay, finally, just like everything else, we have a precise definition for an infinite limit at infinity. So the precise definition is, let f be a function defined on some interval from a to infinity, then the limit as x approaches infinity of f of x equals infinity means that for every positive number m, there's a corresponding positive number n such that f of x is greater than m whenever x is greater than n. So you can see how this corresponds to everything else we've been doing. Either the limit is approaching some specific point by getting closer and closer to a specific value, or it's going away by getting larger and larger. And the same definition is true with minus infinity. Okay, that is it for horizontal asymptotes for limits at infinity. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.